Stochastic processes, Module 9, branching processes. In the Module 1, we have discussed a review of probability. Module 2, we have introduced the stochastic process. Module 3, we have discussed the stationary processes. Module 4, we have discussed the discrete time Markov chain. Module 5, we have discussed the continuous time Markov chain. In the Module 6, we have discussed the martingale. Module 7, we have discussed about Brownian motion or Vernier process. Module 8, we have discussed the renewal process. In this module, we are going to discuss the branching processes. It covers 2 lectures. In these 2 lectures, we are going to cover the definition and examples of branching processes. 2 important branching processes, Galton-Watson branching process and Markov branching process are going to be discussed. Important measures like perform probability of extinction, limit theorem, limit distribution and mean of branching process will be discussed. In the lecture 1, we are going to start with the introduction to branching processes. Followed by that, we are going to start the Galton-Watson process. Few examples will be discussed. Then we are going to discuss the probability generating function of Galton-Watson branching process. Then we are going to discuss the criticality and probability of extinction. Watson in 1974 presented a solution to the problem of extinction of families, which is as follows. Let P0, P1, P2 be the respective probabilities that the man has 0, 1, 2 and so on sons. Let each son have the same probability for sons of his own and so on. What is the probability that the male line is extinct after R generations, and more generally, what is the probability for any given number of descendants in the male line in any given generation? Watson gave the solution. Every family will die out even when the population size on the average increase from one generation to the next. Galton prefaced to the solution by Watson, and Galton recognized that a first step in studying the hypothesis would be to determine the probability that the ordinary family will disappear using fertility data for the whole population. The mathematical model of Galton and Watson is known as a Galton-Watson branching process. In 1938, Kolmogorov was also treated the above problem and determined the asymptotic form of the probability that the family is still in existence after a large finite number of generations. The branching process is a system of particles or individuals or cells or molecules which live for a random time and at some point during lifetime or at the moment of death produce a random number of progeny. Processes allowing production of new individuals during a parent individual's lifetime are called the general branching processes. Examples: populations of higher organisms like vertebrates and plants. Processes that assume a production of progeny at the terminal point of the parent entity's lifetime are called the classical branching processes. Examples: populations of biological cells, genes or biomolecules. One of the important notions in the theory of branching processes is that of the type space. The type space is the set which can be finite, countably infinite or continuum of all possible varieties of particles including in the process. Particles of a given type may produce particles of a different types. Restrictions on the type transitions as well as on the type space lead to different properties of resulting processes. Now we are going to discuss the classical branching processes. Consider a classical branching process in which progeny are born at the moment of parent's death. The distribution of particle lifetime tau has much impact on the behavior and analysis of the process. If tau is equal to 1, then it is called a Galton-Watson process. If tau is exponentially distributed random variable, then the resulting process is called a Markov branching process. In this model, we are going to discuss in detail Galton-Watson process and Markov branching process. If tau is an arbitrary non-negative random variable, the resulting process is called age dependent or Bellman-Harris process. Now we are going to discuss Galton-Watson process. In the next lecture, lecture 2, we are going to discuss Markov branching process. Consider particles that can generate additional particles of the same kind. An initial set of particles which we call the 0th generation having offspring that are called first generation, their offsprings are the second generation, and so on. We denote by Z0, Z1, Z2 as the number of particles in the 0th, 1st, 2nd generations. Please see the illustration. This is Z0, Z1, Z2 and so on. So, this is a illustration of the number of particles in the first generation, 0th generation, first generation, second generation and so on. Furthermore, we make the following assumptions. If the size of the nth generation is known, then the probability law governing later generations does not depend on the sizes of generations preceding the nth. It means the sequence of random variables Zn form a discrete time Markov chain. We make additional assumption that the transition probabilities for the Markov chain do not vary with time. It means the sequence of random variables Zn is a time homogeneous discrete time Markov chain. We have discussed the discrete time Markov chain in the module 4 in detail. Note that the number of offsprings born to a particle does not depend on how many other particles are present. Also, we assume that Z0 is equal to 1. In the illustration also, we made it Z0 is equal to 1, Z1 is a random number of particles, Z2 is a random number of particles and so on. If Zn is equal to 0, then the probability of Zn plus 1 equal to 0 is equal to 1. The probability distribution of Z1 is given by, the probability of Z1 takes a value k, that is nothing but in notation p suffix k, and the summation of pk's is equal to 1, where pk is the probability that a particle existing in the nth generation has k offsprings in the n plus 1th generation. So, this is the probability mass function for the random variable Z1. It is assumed that pk is independent of the generation number n. The conditional distribution of Zn plus 1 given Zn is equal to k is appropriate to the assumption that the different particles reproduce independently. That is, Zn plus 1 is distributed as the sum of k independent random variables, each distributed like Z1. Since the sequence of random variables Zn is a time homogeneous discrete time Markov chain, the one-step transition probabilities are given by p suffix I comma j, that is nothing but the probability that Zn plus 1 is equal to j given Zn is equal to I. That is same as y1 plus y2 plus and so on plus yi, that takes a value j for I comma j belonging to 1, 2 and so on, where yi's are IID random variables, each distributed like Z1. So, the illustration for the Galton-Watson process is Z0 is equal to 1, Z1 here it is 4 and Z2 is 7 and so on. Now, let us consider a simple example. Consider the Galton-Watson process Zn with offspring distribution Pk. Assume that P0 is equal to 1 by 5, P1 is equal to 3 by 5 and P2 is equal to 1 by 5. So, this is the probability mass function for the random variable Z1. Our interest is to find out the conditional probability P, probability of Z2 is equal to 3 given Z1 was 2, and also probability that Z2 is equal to 2 given Z2 was 3, and also what probability of Z2 is equal to 2. So, the conditional probability P Z2 is equal to 3 given Z1 is equal to 2, that is same as probability of y1 plus y2 equal to 3. That is possible either y1 is equal to 0 or y2 is equal to 3, or y1 is equal to 1, y2 is equal to 2, or y1 is equal to 2 or and y2 is equal to 1, or y1 is equal to 3 and y2 is equal to 0. Since yi's are IID random variables, you can write down this as a probability of y1 is equal to 0 into probability of y2 is equal to 3 and so on. Probability of y1 is equal to 0, that is nothing but P0. Probability of y2 is equal to 3, that is nothing but P3. Similarly, the second expression is P1 into P2, third one is P2 into P1, the last one is P3 P0. Since P3 is equal to 0, the first term and the last term will be 0. So, you will get a P1 P2 plus P2 P1, that is same as 6 by 25. So, this is the conditional probability of P of Z2 is equal to 3 given Z1 is equal to 2. Similarly, one can find P of Z3 is equal to 2 given Z2 is equal to 3. That is possible when y1 plus y2 plus y3 is equal to 2. So, the probability of y1 plus y2 plus y3 is equal to 2 we have 6 possibilities. Substitute the value of P0, P1, P2, you will get the numerical value of this conditional probability. Similarly, one can find the probability of Z2 is equal to 2 also. Probability of Z is equal to 2 is same as probability of Z2 is equal to 2 given Z1 is equal to 0 multiplied by probability of Z1 is equal to 0 plus the combination with the probability of Z1 is equal to 1, probability of Z1 is equal to 2. Substitute the values, then you will get the probability of Z is equal to 2. Now we are going to discuss the probability generating function for the branching process. Let yi's be IID random variables, each having the same distribution like Z1. Let h of s be the probability generating function of yi's. Let hn of s be the probability generating function of zn. Since z0 is equal to 1, you will get h0 of s is same as s. Now our interest is to find out the probability generating function for z1. That is same as the probability generating function of yi's. The probability generating function of yi's is h of s, therefore h1 of s is same as h of s. Our interest is to find out the probability generating function for zi, zn, where n is 1, 2, 3 and so on. This we are going to give it as a theorem. Hn of s, this is nothing but the probability generating function for the random variable zn is same as h of n minus 1 of h of s. And hn of s also can be written in the form of h of hn minus 1 of s. Let us see the proof for this. You know that probability of zn is equal to k, that is nothing but summation over i's probability of zn is equal to k given zn minus 1 is equal to I multiplied by probability of zn minus 1 is equal to I. You know that this conditional probability is nothing but probability of y1 plus y2 and so on plus yi is equal to k multiplied by probability of zn minus 1 is equal to I. Now we will go for finding out the probability generating function for the random variable zn. Substitute probability of zn is equal to k from above in this equation. Therefore, you will have a summation of k, substitute the probability of zn is equal to k, that is nothing but the summation over I, probability of conditional probability multiplied by probability of zn minus 1 is equal to I multiplied by s power k. Substitute the conditional probability is nothing but the probability of y1 plus y2 plus so on yi is equal to k into s power k. Since yi's are IID random variables and the probability generating function of yi's are nothing but h of s, the probability generating function of sum of I random variables yi's, that is nothing but h of s whole power I, because of yi's are IID random variables and the probability generating function of yi is equal to h of s. Therefore, the probability generating function of y1 plus y2 and so on plus yi is h of s whole power I. Therefore, substitute this is nothing but the probability generating function of y1 plus y2 plus and so on plus yi. Therefore, hn of s is nothing but summation over k hn of S is nothing but a summation over I probability of Zn minus 1 is equal to I times h of s whole power I. Replace this by h of s whole power I. Therefore, summation I probability of Zn minus 1 is equal to I h of s whole power I. So, that is nothing but the probability generating function for the random variable Zn minus 1 with the replacement s by h of s. Therefore, hn of s is nothing but hn minus 1 of h of s. So, the first part is proved. Hn of s is same as hn minus 1 of h of s. Now, we are going to prove the second part. We know that h1 of s is h of s, that is same as h of h naught of s, because h naught of s is nothing but s. Suppose this is true for n is equal to j, that means h of j of s is h of j minus 1 of s, then we can find out what is h of j plus 1 of s. That is nothing but hj of h of s, that is same as h of j minus 1 times h of s, that is same as h of j of s. By induction, it is proved. Now, we are finding the moments of Zn. Let mu is equal to expectation of Z1 and sigma square is nothing but the variance of Z1, then expectation of Z of n, that is mu power n, and the variance of Zn will be, for mu equal to 1 it is n times sigma square, for mu is not equal to 1 it will be mu power n minus 1 times mu n minus 1 times sigma square divided by mu minus 1. We will prove the part 1, that is expectation of Zn is equal to mu power n. By theorem 1, you know that hn of s is same as hn minus 1 times, by theorem 1 we know that hn of s is hn minus 1 of h of s. Then differentiating and putting s equal to 1, we will get hn dash of 1, that is same as hn minus 1 dash of h of 1 into h dash of 1. We know that h of 1 is 1, h dash of 1 is mu. Therefore, for n is equal to 1, 2 and so on, you will get hn dash of 1 is same as hn minus 1 dash of 1 into mu, that is same as hn minus 2 dash of 1 into mu square and so on. Therefore, you will get mu power n, because you know that h dash of 1 is mu. By recursively, you will get h n dash of 1 is mu power n. Therefore, expectation of Zn is nothing but h n dash of 1, that is same as mu power n. So, till now we have discussed the probability generating function of z power n, and also we have discussed the mean and variance of z of n. As a remark, if mu is equal to 1, the expectation of Zn tends to 1, whereas the variance of Zn tends to infinity as n tends to infinity. You can see it from this theorem. As mu tends to 1, expectation of Zn will tends to 1, whereas the variance tends to infinity, because that is same as n times sigma square. Therefore, as mu tends to 1, the variance of Zn tends to infinity as n tends to infinity. Whereas, if mu is less than 1, the expectation of Zn tends to 0 and the variance of Zn will be sigma square divided by 1 minus mu as n tends to infinity. Similarly, if mu is greater than 1, then the expectation of Zn will tends to infinity and the variance of Zn tends to infinity as n tends to infinity. This also you can see it from the theorem. Now we are going to discuss the criticality. A very important classification is based on mean progeny count mu is equal to expectation of Z1. A very important classification is based on the mean progeny count mu is equal to expectation of Z1. You know that expectation of Zn is equal to mu power n. Just now we have proved it in the theorem 1. Therefore, in the expected value sense, the process grows geometrically if mu is greater than 1, stays constant if mu is equal to 1, and decays geometrically if mu is less than 1. From the expectation of Zn is equal to mu power n, we can conclude if mu is greater than 1, the process grows geometrically. If mu is equal to 1, then the process stays constant, whereas if mu is less than 1, the process decays geometrically. Thus, three cases are called supercritical, critical and subcritical respectively. That means if mu is greater than 1, then the process is called supercritical. In this case, the expectation of Zn tends to infinity. When mu is equal to 1, the process is called critical, and expectation of Zn is equal to 1 as n tends to infinity. When mu is less than 1, the process is called subcritical, and expectation of Zn will tends to 0 as n tends to infinity. Now we are going to consider the second example. Consider the Galton-Watson process Zn with the offspring distribution Pk. We choose the same problem, example 1, with the assumption P0 is equal to 1 by 5, P1 is equal to 3 by 5 and P2 is equal to 1 by 5. Now we can find out the mean of Z1, that is nothing but 1, because P0 is equal to 1 by 5, P1 is equal to 3 by 5, P2 is equal to 1 by 5, we will get mean of Z1 will be 1. Hence, this process is called a critical Galton-Watson process because mu is equal to 1. You can find out the variance of Z1 also. First, you find out expectation of Z1 square, that will be 7 by 5. Hence, variance equal to expectation of Z1 square minus expectation of Z1 whole square, that will be 2 by 5. Since you know mu and sigma square, using the theorem 1, you can find out the moments of Zn, first and second order moment, expectation of Zn and variance of Zn. Since mu is equal to 1, the expectation of Zn will be 1, variance of Zn will be n times sigma square. In this problem, the sigma square is 2 by 5. Therefore, mean of Zn is 1, variance of Zn is 2n by 5. Now, we are going to discuss the very important concept called probability of extinction. If Zn is equal to 0 for some value for n is greater than or equal to 1, then Zm will be 0 for all m greater than or equal to n. And also, the conditional probability of Zm is equal to 0 given Zn is equal to 0, that will be 1 for all m greater than or equal to 1. We say that the branching process is extinguished when probability of Zn is equal to 0 will be 1 for some value of n. Now we discuss the probability of extinction in theorem 3. If mu is less than or equal to 1, then the probability of extinction is 1. If mu is greater than 1, then the probability of extinction is the positive root less than unity of the equation h of s equal to s, where h of s is the probability generating function of a z1. Here we consider a Galton-Watson branching process Zn with offspring distribution Pk, and the Pk forms a probability mass function for the random variable Z1. If mu is less than or equal to 1, then the probability of extinction is 1. If mu is greater than 1, then the probability of extinction is the positive root less than unity of the equation h of s equal to s. That means you have to solve the equation h of s equal to s. From that you can get the probability of extinction. Here mu is a mean of the random variable Z1. Let us see the proof. Let dn be the probability that extinction occurs at or before the nth generation. Hence, dn is nothing but the probability of Zn is equal to 0. We know that d naught will be 0, because we made the assumption z naught is equal to 1. Now we will find out dn plus 1. dn plus 1 is nothing but, by the definition, it is dn plus 1 is nothing but probability of Zn plus 1 equal to 0. We can write a probability of Zn plus 1 equal to 0 using conditional probabilities. That is same as probability of Zn plus 1 is equal to 0 given Zn was 0 multiplied by probability of Zn is equal to 0 plus probability of Zn plus 1 is equal to 0 given Zn is not equal to 0 multiplied by probability of Zn is not equal to 0. We know that probability of Zn plus 1 is equal to 0 given Zn is equal to 0, that is equal to 1. Therefore, this will be 1 times the probability of Zn is equal to 0 plus probability of Zn plus 1 is equal to 0 given Zn is not equal to 0 multiplied by probability of Zn not equal to 0. Obviously, this will be greater than or equal to probability of Zn is not equal to 0, because you are adding some probability plus probability multiplied by probability of Zn is not equal to 0. Therefore, this quantity will be greater than or equal to probability of Zn not equal to 0. This quantity will be, this is same as 1 times probability of Zn is equal to 0 plus probability of Zn plus 1 equal to 0 given probability of Zn is not equal to 0 multiplied by probability of Zn is not equal to 0. Obviously, this quantity will be greater than or equal to 0, the second term. Therefore, the whole result will be greater than or equal to probability of Zn equal to 0. You know that probability of Zn is equal to 0 is nothing but dn. Therefore, dn plus 1 will be greater than or equal to dn. This is true for n is equal to 1, 2 and so on. Hence, the d naught will be 0, d naught is less than or equal to d1, d1 will be less than or equal to d2 and so on. And since the dAs are the probability of extinction, therefore, that will be less than or equal to 1. Hence, dn is a sequence and upper bound sequence. Dn is a increasing and upper bound sequence. There exists d that is nothing but the limit n tends to infinity of dn, and the d is belonging to the closed interval 0 to 1, and d is the probability of extinction of the process. Now we will find out what is the d. You know that dm is nothing but probability of zm equal to 0, that is nothing but summation over j probability of zm is equal to 0 given z1 is equal to j multiplied by probability of z1 is equal to j. You know that probability of z1 is equal to j is nothing but pj, therefore the dm is nothing but summation over j probability of zm is equal to 0 given z1 is equal to j multiplied by pj. We know that probability of zm is equal to 0 given z1 is equal to j is nothing but probability of y1 plus y2 and so on yj is equal to 0. Since yi's are IID random variables, that is nothing but probability of y1 is equal to 0, y2 is equal to 0 and so on, probability of yj is equal to 0. That is same as the probability of zm minus 1 equal to 0 whole power j, that is nothing but d suffix m minus 1 power j. Hence, you can substitute this result in this equation. This conditional probability is nothing but d suffix m minus 1 power j, therefore dm will be summation over j d of m minus 1 power j pj, and that is nothing but the probability generating function of dm minus 1. So hence we get dm is equal to h of dm minus 1. Since dm tends to d as m tends to infinity, the value d satisfies the equation s is equal to h of s, because dm is equal to h of dm minus 1, therefore the value d satisfies the equation s is equal to h of s. Note that the solutions to the equation s is equal to h of s represents intersections of the graphs of y is equal to s and y is equal to h of s. So the d will be probability of extinction, and we are not going to discuss further more about how to solve s is equal to h of s and finding the probability of extinction. We will consider the third example. Zn be the sequence of random variable which is a Galton-Watson process with the offspring distribution pk. Similar to the example 1 and 2, p0 is equal to 1 by 5, p1 is equal to 3 by 5, p2 is equal to 1 by 5. Already we got the mean of z1, that is equal to 1, therefore this is a critical Galton-Watson process. Now we can find out the probability generating function of z1. Using this, one can find the probability of z is equal to, or we can find the distribution of zn also. For instance, we find a probability of z is equal to 2. For that you need the probability generating function of z2. That means you should know what is the probability generating function of h2 of s. With the help of h1 of s and h of s, one can find the h2 of s. That is what we have proved it in the theorem 2. hn of s will be hn minus 1 of h of s. So here we put n is equal to 2, find the probability generating function of z2. Using the probability generating function of z2, we are finding the probability of z2 is equal to So, probability of Z is equal to 2 will be H2 double dash of 0 divided by 2 factorial. So, first you find out H2 of S, that is nothing but H1 of H of S, that is same as H of S. So, replace S by H of S in the H of S expression, that is 1 by 5 plus 3 by 5 times S plus 1 by 5 S square. So, replace S by H of S, so you will get H2 of S. Once you know the H2 of S, you differentiate twice, then substitute S is equal to 0, then divide by 2, you will get the probability of Z2 is equal to 2. Since mu is equal to 1, this is a critical Watson process. By using theorem 3, we conclude the probability of extinction is 1. Theorem 3 says if mu is less than or equal to 1, then the probability of extinction is 1. So, since in this problem the mu is equal to 1, hence by theorem 3 the probability of extinction is 1. So, in this lecture we have covered the definition and the examples of a branching process. In particular, we have discussed the Galton-Watson discrete branching process. We have discussed the probability generating function of Zn. We have discussed the mean and variance of Zn. Also, we have seen 3 examples through that we found the conditional probability, probability generating function, mean and variance of Zn. Finally, we have discussed the probability of extinction for the Galton-Watson process. In the next lecture, we are going to cover the another important branching process, that is a Markov branching process, which is a continuous type branching process. In this lecture, we have discussed a discrete type branching process, that is a Galton-Watson process. In the next lecture, we are going to cover continuous type branching process, that is a Markov branching process, and some more important branching processes. Here is the references.